Good morning. Today we're going over our first homework assignment for matter, which includes atoms and elements, periodic table, that kind of thing. So let's get started. First question here is asking about modern atomic theory, and the statements regarding modern atomic theory were given by John Dalton, and these are the things that you need to be aware of. Number one, all matter is composed of atoms. Number two, one element differs from other elements. Number three, compounds are combinations. Each molecule of the same compound has the same number and type. And lastly, atoms can't be created or destroyed by chemical reactions. So we've got a number of statements here. This is showing, say, chemical reaction, and we see we have the same number of calcium atoms on both sides and carbon atoms and oxygen atoms, so nothing was created or destroyed, so that would be appropriate. Here it's comparing nitrogen with carbon and how they have the same mass because they've got that little upper left-hand corner there. Here we go. If we scroll down, we talk about the contents of atoms. They've got protons and neutrons, and they can have different masses, and all of your masses come from protons and neutrons. So that's totally fine. Different possible compounds of carbon and hydrogen. Those look appropriate. These behave differently because they are, in fact, different atoms. They have a different number of protons. This is problematic. 3.5 carbon atoms, 3.5 oxygen atoms. You cannot have half of an atom. They only exist in whole numbers. Next, symbols for the following elements. Let's pull up our periodic table that we use for our exams. I can scroll in here. Oxygen is O. Vanadium is V right here. Note that they all have capital letter, even those with two letters. The first one is capital and the second one is lowercase. And that's important because having CO with capital C and lowercase o is different than CO with capital C and capital O would indicate that it has both a carbon and an oxygen rather than one cobalt. Phosphorus is capital P. Now you don't have to memorize these because again you will get this periodic table with the names of these compounds on your exam, but it's nice to kind of be exposed to this and familiarize yourself with where things are. Manganese, capital M, lowercase n. Hydrogen, capital H. Neon, capital N, lowercase e. Tin is right here, capital S, lowercase n. And silver right here, capital A, lowercase g. So many of these are what you would expect. Neon has the first two letters, Ne, and so are not what you would expect. Tin having letters Sn, that's referring to a Latin form of that metal's name. Now to go backwards, if you give the symbol, then can we find the name? He stands for helium. Capital P stands for phosphorus. I can spell. Na stands for sodium. Mg stands for magnesium. You may have different symbols and different names on these particular questions. Just look on the periodic table. One thing to note, cesium is C-E-S-I-U-M. Aluminum should not have that I, should just be aluminum, N-U-M, not N-I-U-M. This periodic table that I give you is actually appropriate for the British English spellings, but Master in Chemistry will test you on the American English spellings. All right, the remaining, we've got Ca, that's calcium. Br, that's bromine. Cd, that's cadmium. And Si, that's silicon. Not silicone, but silicon. All right, match the properties with the appropriate subatomic particle, and that brings us back to this part of our lecture notes. Proton has got the symbol P, neutron symbol N, electron symbol E. Neutron is neutral, so it has no charge. The electron has the -1 charge, and the proton has the +1 charge. By mass, what we have here, Electrons are 0, neutrons and protons are 1. So these are about 1. And they're not actually 0, but it's so small with reference to the significant figures that we're generally working with, it's basically 0. Okay, which one has a mass about the same as the protons? Neutrons and protons both have a mass about 1. Protons and neutrons are found in the nucleus. It's this section right here. Larger part of the atom, that's the electron cloud. And the electron carries the negative charge. In a neutral atom, because electrons have a negative charge and protons have a positive charge, if I'm neutral, then I have to have the same number of protons and electrons. That way their charges cancel out. If I have an ion with 109 electrons, 158 neutrons, and a +1 charge. All right, let's work this out. I have some ion, X, with a charge of +1. And I have neutrons, 158, and electrons, 109. Now the protons, because I have a positive charge, that means I have one more positive charges than I have of negative charges. So if I have 109 negative charges, I must have 110 positive charges in order to be left with a positive charge. So then the total mass must be the number of neutrons, which they gave me, plus the number of protons, which we had to deduce based on the charge. So 158 plus 110 gives me 268 for my mass. Next, identify the following atoms based on number of protons. Number of protons defines an element. That is this little number at the top here, which is known as the atomic number, is also the number of protons in the nucleus by definition. So if I have 21 protons, then I am element number 21, or element with atomic number 21. That makes me scandium Sc. Now if I have 51 protons, then I am atomic number 51, and that makes me antimony, that is Sb. And Z is another term for the atomic number. So if I have Z atomic number 30, that makes me zinc, Zn. I don't use the Z notation in exams, but there it is. Okay, isotopes have different masses, but they have the same atomic number. That is, your atoms of the same element, but you have slightly different masses because you have different numbers of neutrons. So we're going to write those using the symbol with the AB above it to show the top number as the mass number, the bottom number as the atomic number is what they're telling me. So they want us to write the notation for an isotope with 8 protons, 8 electrons, and 11 neutrons. So this is telling me it's neutral, and the total mass, because the positive charges are equal to the negative charges, and the total mass is protons plus neutrons, so it is 19. So this is an element with a mass of 19 and 8 protons. And by definition, if I have 8 protons, then I am oxygen. Now, here are boxes for 3 different isotopes of nitrogen. They are all nitrogen, so they all have 7 protons. But what changes is the number of neutrons. If you have 7 protons plus 7 neutrons, that gives me a mass of 14. So here we go. If I have 7 plus 8 neutrons, that would give me a mass of 15, and 7 plus 9 neutrons would give me a mass of 16. Mass numbers listed on the top. So mass number 14, 15, 16, 14, 15, 16. Isotopes of the same element would have the same atomic number, which is listed down here. So 11, 13, 11, and 12, the 2 that both have the atomic number of 11 would be the same element. And then they have different masses, 19 and 21, that makes them different isotopes. The isotope symbol for 209 bismuth is right here. It's element number 83. So by definition, that atomic number that goes on the bottom is 83. In this case, we're told we have an element with a mass number of 238 and an atomic number of 92. By definition, the element with an atomic number of 92 is uranium. Next, we have an isotope with a mass number of 197 and an atomic number of 79. If I have an atomic number of 79, then by definition I am gold, because gold is element 79. And lastly, we have Br, which is bromine. And I have a mass of 79, and they want to know the atomic number. If I look here, by definition, bromine is 35. Just plug that in. All right, next. Same thing, but they're giving us the information in a different form. So if I have 8 protons and 10 neutrons, then my total mass is 18. The 8 protons gives me an atomic number of 8. And then I look up here, that makes it oxygen. In this case, my mass number is 43. Number of protons, which is the atomic number, is 20. Element number 20 is calcium. Next, if I have a mass number of 20 and 10 electrons, we're talking about atoms, not ions. So atoms are neutral, which means it has 10 protons as well. It's a tricky way of trying to tell us that it has 10 protons and 10 electrons. That would be neon. Which of the following represents a pair of isotopes? Isotopes have to be the same element, so carbon and nitrogen don't count. They have to have different masses, so sulfur 32 don't count. These are different atoms with the same mass. These are different ions of the same element. These two are isotopes because they are the same element, but they have different masses, mass of 1, mass of 2. And these are 2 different compounds made with oxygen. An atom with a mass number 58 and 32 neutrons has how many protons? Well, because your mass comes from your protons and your neutrons together, this is a simple mathematical calculation. Mass of 58 minus 32 mass that came from the neutrons means that 26 of that mass came from the protons. So that's how many protons you have. Now, the masses that are listed here are average weighted for abundance. You can't have half of a chlorine atom, and protons and neutrons have a mass of 1 each. So how do you get half of a mass? Well, it's because you've got some chlorine with a mass of 35 and some chlorine with a mass of 37. On average, when you weight for the abundance of each of those isotopes, you come up with this particular mass number. So here's how this is done. We see we've got chlorine 35, which has 34.97. It's not exactly 35. And we have chlorine 37, which is 36.97. And what we have is 13.85% of this. So that's a fraction of 0.1385 and 86.15% of this. So 0.86. So the mass is multiplied by its fraction, and this mass is multiplied by its fraction, and we add it up. That's how we do it. So we have 34.97 times 0.1385 plus 36.97 times 0.8615. And we get an average mass weighted, this is the weighting for abundance, of 36.69. Now taking just the average would add them up and then divide by 2, or basically multiply this by 1/2, multiply this by 1/2, and then add it up. So this is where the weighting for abundance, rather than multiplying them each by 1/2, which would indicate that they are equally representative, then we give the actual representation here. So here's another example. And now we have 3 different masses at 3 different abundances. And again, because this is a percentage, we're going to move that decimal place over to make it a fraction when we multiply through. So we're going to have a mass of 27.98 multiplied by its abundance, 0.7371. Add to that a mass of 28.98 multiplied by its abundance, 0.1493, plus a mass of 29.97 multiplied by its abundance of 0.1136. And that gets me an average mass weighted for abundance of 28.36. Now, if you do this, you must get a mass which is in the range of these masses, right? Because it's not exactly an average, it's a weighted average, but it's going to be, say, lower than the highest mass and higher than the lowest mass. Same thing here. So if you make a mistake and you end up outside of that range, then you'll know you made a mistake because your mass will be far out. Here's another one. Give me masses for these particular iron isotopes, and then they give us weighted fractions of each of these. And now we need to find the average mass of iron weighted for abundance. So 54 is 53.940. Multiply that by its abundance, which is 5.82%, 0.0582. And then for iron 56, which has a mass of 55.935, going to multiply it by its abundance, which is 91.66% of the sample. Then we've got iron 57, which is 2.19. It has a actual mass of 56.935. 2.19% as a fraction of 0.0219. And finally, we have iron 58, which is 57.933. We're going to multiply that by its abundance, which is 0.33%, which is 0.0033 as the fraction. All that comes together and I get an average mass weighted for abundance of 55.847. And it should be the closest to this one right here, because that was more than 90% of my sample was iron 56, which has a mass of 55.935. So you can see, yeah, I'm actually pretty close to that. All right, same type of question, but now in a multiple choice format, and now giving me imaginary element XZ. I've got two isotopes. I've got XZ with a mass of 100. And I have XZ mass of 102. And this is actually 100.0, 102.0. And they're saying that this is 75%, so that's 0.75. This is 25%, so that's 0.25. I'm going to add those together just like I did on our last example. So we have 100 times 0.75 plus 102 times 0.25 gives me average mass weighted for abundance of 100.5 atomic mass units. That's it. I hope this was helpful. Have a great day.